Lesson. So the concept of momentum and impulse, and where have you heard, well first of all, where have you heard the term momentum before? Momentum. Give me an example of what momentum would mean to you.
Like something picking up momentum, what
does that mean, picking up momentum?
Okay, I'm going to use it in a non-scientific term, that's fine. A stock is picking up momentum, that something is, it was not in motion, or was in a slower rate of motion, and starting to pick up and roll and started getting FOMO.
It's a great example of stock. It picks up momentum, meaning it starts to gain value, right? So you're getting back to what you said, which was a rate. That's the key word there, rate. And a rate that we know of is velocity. Physics-wise, momentum, we're really talking about mass and velocity. That's what we're referring to. But the idea of momentum is that something is picking up like a snowball going downhill. Ever see like those cartoons where the snowball gets bigger and bigger and bigger as it falls down the hill? It's gaining mass. And because it's going downhill, it's also gaining velocity. Remember, it's losing potential energy because it's going downhill, but it's gaining kinetic energy. It's also gaining mass because the snowball is getting bigger and bigger and bigger. So the idea is that it picks up momentum. Momentum is a function of those two things, mass and velocity. What else was a function of mass and velocity? What else? We just studied. It's a function of mass and velocity. What parameter or what entity was mass and velocity related to? Think about your formulas from last chapter. What are your formulas from last chapter? Which one involved mass and velocity? So, kinetic energy. So what we're going to see in this chapter is that we're going to utilize the concept of kinetic energy hand in hand with momentum. We're going to have to talk about kinetic energy, whether or not it's conserved. If kinetic energy is conserved, we talk about the collision being a certain type of collision. If kinetic energy is not conserved, it means you lose energy to thermal energy or heat. So let's take a look at this real quick. So very simple. These carts are on a track. And the cool part about this track is it simulates a friction in the surface. And you can kind of see that. Look at this. I barely touch these carts, and they move very easily. The wheels on them spin very nicely. Now, it seems that way, but over time, believe it or not, they get a little bit less and less, they gain more friction in the wheels themselves. So on these carts, we're going to see first of all, there are magnets on the end that you can utilize to help cause the carts to stick together. There are these little spring-loaded mechanisms here in the carts. The spring load we'll talk about what we're going to do with. And then we'll also see that, let's see yeah, we can take these spring-loaded mechanisms and contract them, so you can press this button, and what happens as a result, it expands so it uses its potential energy in the spring. So, simply put, today we're going to talk about impulse and momentum. We'll see collisions, but the idea is, if I apply a force to something, what should happen? If I apply a force, what happens? Generally, what happens if I apply a force? Better?
The thing should move.
Something should move, right? There should be some acceleration. When there's acceleration, there's a change in velocity. When there's a change in velocity, there's probably some sort of motion occurring. So here in this case, we're going to see this term impulse. And impulse is related directly to your momentum now. So if I were to just press the spring load here, we'll see that this one moved back and this one moved forward. Now, if this were fixed, obviously, springs are break. These are old. If this were fixed against some surface, would you hold this one still? Alright, so if this one were fixed, it cannot move back. So as a result, what we'll see is that this one, as much as it didn't seem like it moved far, moved a lot further than it did a moment ago. When we did a moment ago, we did this. When we did that, this one started moving backward. So the idea is that if an object applies a force to something, the momentum of it is conserved. So if both of them are moving away from one another, they have like half the momentum each in a sense. But if this one is held still and the spring is released, this one will move faster away from it. When two carts themselves collide, if one is moving and one is not, watch what will happen, you see. This one moves and hits that one, what happens to this one now? It stops. What is that? It's a
transfer of energy.
Yeah, it's a transfer of momentum in this case, but energy as well, yeah. So we'll see that we have collisions we're going to talk about in this chapter. When two things collide and one of them stops afterward and the other one moves, it's a certain type of collision. Now, I don't know if which one is polar opposites. Some of these magnets are actually working, some are not. Well, these two you can link together. Let's link these together. So there's also these Velcro on them. Let's see if Velcro's even working. The Velcro's supposed to keep these together. It kind of is. Okay, and what will happen is, if there are two masses, and this one hits it now, you'll see this one will stop, but these two masses did not nearly go as fast as when you did this, when it launched the other one. And now, obviously, I'm changing the velocity by not really doing this in some sort of a fixed way. But the idea of this spring mechanism here, you're going to have the exact same amount of energy every time. So what we're going to do in this chapter is we're going to do a few labs. We're going to do two labs. One will be with this, and one will be with a simulation of these two concepts of momentum and impulse. They're going to govern the entire chapter, the concepts of momentum and impulse. We're going to see where the math is going to be related in this section. Okay, so to give you an idea of what we're going to do with it, so you have an idea or some knowledge. So we spoke about this a moment ago, but so you know formula-wise, P is equal to mv. Lowercase p stands for momentum. Lowercase p stands for momentum. Capital P was what? Anybody remember what capital P was? Capital P was power. Now, the reason that we have this term P is because a long time ago, scientists used to not call the word momentum, they called it progress. How much progress it makes. In progress, you think about progress, it's like, you know, how far you get through a task or a job. Like, how much progress have you made on your homework? Well, if you've made a lot of progress, you could say your momentum carried you through that homework. So the term progress was used back with Leibniz and Newton. So the term P was used for momentum. It's not power. So lowercase p, and it means momentum. And clearly you can see here that momentum is the product of mass and velocity. There are no simplified units for momentum. Every chapter so far we've had some sort of new unit we've introduced. Last chapter, energy, what were the units? That was power, good. And energy was just? Yeah, just joules. So we had joules and we had watts last chapter. Now we're looking at this and we can see that mass is kilogram and then velocity is meters per second. There is no simplified unit for it. So if you told me how much momentum an object has, you could say 7 kilogram meters per second. You just read the unit right off, kilogram meter per second. Okay? So it's obvious, and I hope by now you guys are good enough at this concept of direct and indirect relationship, that as mass picks up, momentum picks up. As velocity picks up, momentum picks up. Okay, but momentum is conserved, and we're going to see how that works in the next section with conservation. For today, we're going to take a look specifically at momentum, and then we're going to go into our term or our topic of impulse. Okay, our topic of impulse. Now, if we want to discuss what impulse is, okay, we could start with a little derivation we're going to use. So let's begin this. So let's take this formula we have here, okay, and let's rewrite it as the change in momentum equals mass times the change in velocity. I'm going to show you a little remember the derivation we did to come up with power equals F times speed? We just plugged in some formulas and simplified. We're going to do the same thing here. We did that as well for the work kinetic energy theorem. So for this, let's go ahead and divide both sides by time first. Let's divide both sides by time. So on the left-hand side, we've got delta P over T. On the right-hand side, we've got M times delta V over T. What is delta V over T?
Acceleration.
Delta V over T is acceleration. That's right here. So we could write that delta P over T equals mass times acceleration. Because delta V is change in velocity. The change in velocity with respect to time is always your acceleration. But what's mass times acceleration? What's mass times acceleration? Think back a couple of chapters ago.
Force?
Yeah, very good, because F equals ma. So we can replace that with net force, or force. Now, what we do next is we say, okay, let's solve for delta P. How would I solve this for delta P? What do I have to do to get delta P by itself? We should all have hands up. Pablo, go. How do I get rid of that t if it's dividing? What's the opposite of that? Yeah, multiply it on both sides. So we've got F times t. Okay, so this is what we're going to call our momentum impulse theory. Let's jot that down. Momentum impulse theory. And let's talk about its significance here. Let's talk about its significance. This here, this quantity, is called impulse. And this is your momentum. And it's clearly the momentum change. Right, the change in momentum. So we can see that as our force increases, we have more of a change in momentum. Well, let's make sense of that. I take this card and I go like this. Doesn't move too much, right? But I take the card and go like this, it moves a lot more. I applied a larger force, thus it acquired more momentum as a result. Now, if instead of doing what I did, instead of going like this, ready? Actually, there. Instead of just going like this and applying a force for a quick second, if I apply that same force for longer, what happened? It also acquired more momentum or more velocity. So if I either increase the amount of force I apply, momentum goes up, or if I increase the time period that the force is applied for, momentum goes up. And that makes sense. Think about it. Have you ever pushed a piece of furniture, and as you push it more and more and more, it kind of speeds up? Okay, that's because you're applying that force for a longer time period. Or maybe instead, you're applying that force a lot greater than just lightly tapping it. So your force goes up. But as a result, delta P goes up. And delta P, if you recall from the beginning of this slide, is m times delta V. Do you see any masses changing here? Did I change the mass of this somehow? No. So if the mass isn't changing, delta V must be changing. So although this is the momentum impulse theory right here, what we're going to see is that really, if you want to write it like this instead, okay, it might be more useful to write it like this. Okay, because delta P is m delta V. And I'm not changing the mass, so that can't vary at all. I did not add something to this card. I can do that, right? I can go like this. I could take an object like this expo marker, and I know it's not realistic, I wish it was a little heavier, and throw it on here. See how it barely moved like that? It moved very slightly. It's almost impossible to see, but see how it just moved like that? Well, not only did I give it a little bit of a force, but I also now increased its mass. So that's a little bit different than what I was saying. That would be a change in mass there. And we're going to see that this chapter. We're going to see what happens when, and I don't know if these magnets will work this chapter, but we're going to see what happens when two cards collide and stick together and move as one. Well, now isn't the mass much greater? It's double the mass. Right? If this card was moving by itself initially, and it had some momentum, and it collides, and they stick together and start moving together, well now, it's moving as one entity. So the mass is much greater now. So this might have had a good amount of momentum to start, but now that momentum splits up into both. So what's going to happen is it's going to slow down, obviously. Right? It'll still have the same momentum because momentum is conserved. So this one might have a momentum of like 10 kilogram meters per second. Well, it hits this card, so as a result, they still have 10 kilogram meters per second momentum, but to have that, the mass went up by a factor of 2. So the velocity has to go down by a factor of 2. So if these two cars literally collide, the velocity will cut in half if they stick together. Again, if this has a velocity of 5 meters per second, and these two collide and stick together, now it's going to have a velocity of 2.5 meters per second, or less, because some energy is lost in the collision. Yes? So in a car accident, there's several outcomes. 1, they collide and separate. 2, they collide and fuse together. The reason a lot of cars fuse together in collisions, like the back bumper will hit the front bumper, or the front bumper of one car will rear on the other, they fuse together because the heat between the actual bumpers themselves causes them to melt and fuse to one. That's this right here. That's exactly right. And we're going to see that. We're going to talk about that. Or honestly, sometimes a car will literally get caught underneath the other car. If somebody gets rear-ended, the front end of the car can get actually jammed underneath. And you ever see on the back of a truck the little towing things on the back?
Yeah.
That can sometimes literally go into the front of the other car and literally engage. And the cars will move as one afterward. So as a result, these two things can stick together and they slow down together. But what you'll see is that, and we talked about this in the other topic, the bigger object will not feel it as much because it has more mass, right? It has more inertia than the other one does. And we talked about how that works. Now, if the second object is immobile, it cannot move, and there's a collision, well, that's a whole other story. So let's say, for example, this is a tree, and there's a car, and the car hits the tree, it's going to bounce off. Now, a lot of cars, what will happen, they'll kind of wrap around the tree. Ever heard the term wrap around? It's because the front end of the car kind of compresses forward like an accordion, and the sides of it wrap around the car. And a lot of energy is lost in that collision. But the car itself will rebound a little bit off of it because the tree is immobile. If the tree could be uprooted, though, it's not strong enough, you might see it go like that, and the tree actually starts to move a little bit back. The tree might come out of the ground. Other things like collisions, think about like football players. You see it all the time in football games. It's incredible. Kinetic energy and momentum are the most, frequently occurring type of physics in a football game. Well, obviously velocity and that stuff because you're running, but there are collisions all the time. You see people like, any Jets fans? I forget who the Jets fans are anymore. None?
Yeah.
Oh,
that's okay.
yeah.
I can do it.
I was going to curve the no, kidding, I wasn't. Any Giants fans?
Yeah.
Okay.
Bandwagon.
So there are a lot of running backs that run with speed, a lot of running backs that run with power. So some running backs are able to literally avoid linebackers, avoid defensive linemen, avoid the cornerbacks, whoever the defense is. Some running backs actually seek to run into them. They look for that. I was going to mention Ivory on the Jets because he's one of the guys who always does this. You'll see him lower his shoulder, lower his head, and hit somebody and bounce off, rebound, and continue running. That's like this. He hits them. As he bounces off, he then goes around afterward. But that's an example of a collision where the conservation of those two is conserved. So he might bounce off back a little bit, but he's able to recover and continue on. Obviously, if the one guy tackles the other, then what happens? They stick together, and they both move together, and they fall together. Okay? All right, so the momentum impulse theory tells us, again, that the more force or time you have, the more change in momentum you have. Okay? The more force or the more time that force is applied for, the more change in momentum there is. And that change in momentum is usually a change in an object's velocity. Okay, unless they stick together, then we have a change in mass. So let's take a look. Very similar to the first example we did with kinetic energy, where I said there was a bowling ball and a bouncy ball. Figure out the speed the bouncy ball is to travel with to have the same kinetic energy as the bowling ball. Well, very similar right here now. We have, again, a bullet and a bowling ball. And it says, what velocity must a bullet with a mass of 4 grams have in order to have the same momentum as a bowling ball with a mass of 6 kilograms traveling with a velocity of 8 meters per second? Okay, and these are realistic numbers, by the way. 6 kilograms is, anyone know how many pounds? I've mentioned this conversion factor a few times. 2.2 is your conversion factor. Okay, so 6 times 2.2 will give you 13.2. Okay, so it would be like 13-pound bowling ball, which is realistic. Professional bowling balls are between like 12 and 16 pounds usually. A bullet, about 4 grams. That's about realistic size for a bullet. The speed of a bowling ball, 8 meters per second, is also realistic. It covers 8 meters every second. When you bowl, it only takes like a second or two to get down that lane. The lane is like 30, 40 feet long. That's like 20 or like maybe 10 or 20 meters long. So another realistic value. So if we want to figure out what the actual velocity must be, we have to look at a momentum balance. We have to look to see how will the momentum of these objects be the same. So we've got the momentum of object 1 has to equal the momentum of object 2. That's what we're asking for here. We want them to have the same momentum. So as a result, object 1 is mass times velocity. Object 2 is mass times velocity. There's no before and after yet. We're going to do that in the next section where we have actual collisions, and we'll say momentum before the collision and momentum after the collision. Just like MEI equals MEF, just like conservation of energy, we'll see that in 5.2. But for now, we have just M1V1 equals M2V2. What could you do at this point if you want to? If you want to. Yeah, you could plug in numbers at this point. Okay, you could plug in numbers and solve. You could solve generically. Either way works. Which of them are you going to call object 1? Doesn't matter. The bullet? Okay. So the bullet is object 1. Therefore, the mass of the bullet, which is 4 grams, oops, is really how many kilograms? Okay, we have to have the same units. This is actually one of the sections in the year that it doesn't matter if you use grams or kilograms, but you have to have the same units for both objects. So if you wanted to convert 6 kilograms to 6,000 grams, you could do that. And then your momentum will be grams meters per second instead of kilogram meters per second. But you could keep the units as grams this chapter as long as both objects are measured in grams. But you need to be consistent among all objects in your scenario. All right, so that's the only thing we have to convert. So at this point we could solve. We're trying to figure out the velocity of the bullet. If the mass of the bullet was called m1, then we're looking for v1. If the mass was m1, we are looking for v1. So v1 is going to equal m2v2 divided by m1. So we've got m2, the mass of the bowling ball, times the velocity of the bowling ball, divided by the mass of the bullet. Okay? Again, this is the bowling ball, this is the bullet. You could have plugged in numbers and then divided by the 0.004. It's the same thing as doing it generically. Obviously, you're going to get a number that's much, much, much greater than the velocity of the bowling ball because this is a bullet. For a bullet to have the same momentum as a bowling ball, it's got to be going a lot faster. Frank?
12,000.
Yep. And since I started with meters per second, I still have meters per second. Okay? So it would take a bullet moving at a ridiculous velocity to have the same momentum as a bowling ball. Side note, why is a bullet so much more deadly, though, than a bowling ball would be? Seriously.
It's kind of self-explanatory because it goes a lot faster and it just kind of rips through your body. I mean, I don't know.
It does, but I mean the momentum though of a bowling ball is much greater than a bullet would be. Yet a bullet does a lot more damage than a bowling ball would. Not necessarily dense, but you're on the right track.
It's because it's like smaller and the shape too.
The shape and the size for sure. What's the term? Anybody know the term? We haven't done it yet this year in physics, but there's a term that represents this.
The bowling ball's structure.
Not the structure. I mean, the structure affects it, the size and the fact that it's at the end, yeah.
Is there like less surface area or like it's like more precise?
Yeah, less surface area is the right way to say it. When you have less surface area, what goes up?
The pressure?
The pressure. Think about a pin on a balloon. You take a pin and you touch a balloon, what happens to the balloon? Pops. You take your hand and touch a balloon, does it pop? Lot smaller surface area, right, for a pin? The pressure goes up dramatically, which is what actually causes the membrane of the balloon to burst, because of pressure. So the idea of pressure, we're going to see that later in the year. We're going to get to pressure and talk about that. Okay? All right. So good idea of the first example. Velocity of the bullet must be greater than the velocity of the bowling ball in order for this to have the same momentum, because the mass of the bowling ball is so much greater than that of the bullet. Okay? The momentum impulse theory first. Okay, so we have a 1,500 kilogram car moving with a velocity of 20 meters per second east, and it collides with a tree, comes to rest in 2 seconds. Find the force exerted on the car during this collision. Find the force exerted on the car during this collision. So we're looking for force, so you should think about the momentum impulse theory. We'll start by writing that out. Okay, there's a momentum impulse theory. The question is, what is the change in momentum in this problem? How do I find the change in momentum? Because my goal is to find the force. I've got the time. That's easy. How do I find delta P?
Is it PI minus PF or PF minus PI?
Sure, that works. Final momentum minus initial momentum. We could do that. What else could we have done? What else could I have written? What's the formula for momentum from the last slide? What's the formula for momentum? Emma? P equals mv. Well, m isn't changing in this case. The mass of the car is not changing. Well, maybe, I guess, if you like the glass like shoots off, if it breaks and stuff. But what's really changing is the velocity, right? Because it comes to rest. So we could have also just written it like this. What in reality, that's exactly what Anthony said, though, because this formula here, let's move this up a little bit. This formula here really becomes final momentum, which is m times final velocity, minus initial momentum, which is m times initial velocity. Well, these are the same formulas right here. Delta V means final minus initial. Well, here's final minus initial. So this formula and this formula are the same thing, really. They both become this formula. How does that work if you don't understand it? This one becomes m times Vf minus Vi. And then really, if you look at this, right? So again, this one became this one down here. This formula becomes this right here, but these are the same things. If I distribute this m, don't I get this down here anyway? If I distribute the m in blue, I get what's in red at the bottom down here. Okay, so either way you want to start this problem is fine with me. But the thing is, what is the final velocity in this problem? What is it? What's the final velocity? What's the final velocity? It hits a tree and comes to rest. Zero. As a result, we cross this portion off. This goes to 0. So I've got negative mvi equals f times delta t. What does that indicate to you? What kind of a force are you going to get? What kind of a force are you going to get? A negative force. Why would you get a negative force? How come? Go back to forces and think about what a negative force simply means. A negative force means what? What does it mean? If I'm running this way, right? And there's a negative force or a force that's acting against me, it pushes me back, right? If I'm running this way, and there's a negative force, it means it pushes me back that way. Either way, the concept of a negative force simply means that it's slowing down the object, or it's a resistive force. Just like friction, remember work done by friction was negative. Work done by a force acting in the opposite direction would be negative here. Okay, so we're going to have a negative answer for force. The mass in this case for the car, I think, was 1,500 kilograms. The initial velocity of the car was 20 meters per second east. East is positive, right? Think about east and west. East is positive. So this needs to be positive. So as a result, I can get my force because I know that it took 2 seconds for this to happen. Okay, my force will definitely be negative. It will definitely be negative. It's going to be 15,000, it looks like, right? Negative 15,000. What are my units for force? Newtons. Okay, good timing there. So, in this example, we're told that the soccer ball is moving to the right with a given velocity of 9 meters per second. It collides with the wall, bounces off. The wall exerts a certain amount of force on the ball for a certain time period. The question is to find the velocity of the ball after it hits the wall. So we know that the ball is moving with some velocity, it hits the wall and rebounds. So what kind of velocity should we get as an answer automatically? It's going this way, it hits the wall, and it turns back around. Negative, some sort of negative answer. That's the first thing we should recognize. Okay, so the ball is moving with a positive velocity initially. The velocity to start is given as 9 meters per second. The mass of the soccer ball is 0.5 kilogram. The amount of force that the wall exerts. Now, if the ball is moving with a positive velocity, the wall exerts a force which way? That way. So what is that? Negative. So this force, although it's listed as a positive force, we need to recognize that it's really truly negative. Okay, again, ball is moving to the right, wall pushes back to the left. So clearly it's got to be negative. There we go. I didn't notice your hair this morning. It's nice. It's braided from the top. It's so nice. You went like this, and I just saw it right now. It had you in mentor today. Wow. The time period of contact is 1/5 of a second. Okay, 0.2 seconds. So that makes sense. Think about a soccer ball colliding with a wall. It's only going to be in contact with the wall for a very small amount of time. Now, keeping in mind that the ball itself is probably going to compress a little bit, and then expand back, and then go backward. That's what really happens in slow motion. And feel free to look at that. A lot of you have iPhones with the like slow-mo cameras. You could actually put that camera up and set it up next to something and take a soccer ball or basketball and like throw it into the wall or bounce it. You actually see the compression. You see it very slightly. I mean, you can also just Google, a ball bouncing and compressing. You'll see the ball actually, the shape changing a little bit. What that tells us about this problem, obviously, is that we're losing energy to deformation. And we'll see how that comes into play in section 6.3. We're going to take a look specifically at that kind of stuff. All right, we've got all of our information written down. What are we trying to figure out? Final velocity, VF. Okay, now, if we're given something to do with forces and velocities and and masses and time, there's a good chance that we have some sort of a... What are you going to say? Okay, there's time that's elapsed, absolutely, but what kind of a problem is this, my question?
2 parts.
Okay, 2 parts. We could probably do it in 1 part. Make it a little bit easier. I mean, 2 parts is an initial and final, sure, but mathematically it's only 1 part. Are we going to use our regular momentum formula, P equals mv for this?
No.
Okay, so what's the other one?
Changing momentum, F equals delta P times delta T.
Close.
No.
You just got them backwards, okay? So we're going to use our momentum impulse theory. The change in an object's momentum is equal to the force applied to that object times the time period that it's being applied for. So we know it's being applied for 1/5 of a second. We know that the force is negative 42.5 newtons. We're trying to figure out the final velocity, but I don't see final velocity in this formula. It's not there. Right? I don't see VF anywhere in the formula. So I'm stuck. I can't do this problem, I guess, right? What can I do? Yeah.
Because the change in P is mv1 mvf minus mvf.
Yeah, that's what change in momentum is. Very good. So we start by writing it like that. We recognize, well, momentum is m times v, so the change in momentum is m times delta v, really. Or we could just say mvf minus mvi. The final momentum, mvf, minus the initial momentum, mvi, equals the force times the time period it's applied for. Okay? So at this point in time, we have everything, actually. We could, if we want to, solve generically. We'd have to factor out an m, and then divide through by m, or subtract, and then divide through. Or we could plug in numbers. Okay? I'm going to plug in numbers. I don't do this often. I'm going to plug in numbers at this point. VF is unknown. I leave that alone. The initial velocity given was 9. The force applied times the time period. Okay, solve for VF. Go ahead and solve for VF. If you solve for VF generically and you I guess, prefer that method, it would look like this. Okay, that's what it would look like with a generic solution. You would add the m, oh, sorry, it's a positive. You would add the mvi to both sides and then divide by m to get vf by itself. So if you want to write what's in red, that's what the generic solution would be. But again, solving this, it's the exact same answer. Nick, what do you get?
26 meters per second.
Positive or negative, Nick?
Negative.
Yeah. 26, you said?
Yeah.
Exactly. Okay, it's got to be a negative answer because the ball hits the wall and it rebounds off of the wall. Okay, it hits the wall and it rebounds. Are we sure of this answer? Are we sure? I didn't get negative 26 when I did it, but I could have possibly made a mistake, so please check. Yeah, Nick, I did not get that for sure. Did you? Can you check your work real quick?
42.5.
It's negative 42.5, Nick.
Yeah.
Others get an answer? I think it's something different.
I got negative 27.
Negative what?
27.
Negative 27? I didn't get negative 27 either.
I got negative 26.
Minus 0.8. Yeah.
That's why I keep
Say again?
Wait, if it's,
We're taking 0.2 times negative 42.5. Then we're adding this number here over to this side. And then we're dividing by this 0.5. What do you get? Negative 8. Check your work, guys. I got negative 8 also. Nick, take a look at what you made a mistake.
Oh, I know what I did wrong.
Yeah.
You sure?
I subtracted 4.5 instead of adding.
Correct. You have to add this number because you're adding it to both sides. Okay, good. If you are having trouble getting the algebraic portion done, that's why you are checking it during class. That's why you're asking questions during class. I've said this like at least 1,000 times this year. If you don't check it during class and on the test you can't do it, that kind of sucks, right? So you should always be checking your work, and everybody should be doing this and saying, yeah, Mr. Howell, I got negative 8 that time. That looks great. Or I didn't get that. Could you please explain how you got that? One of those two options, really. Sitting idly by and watching others do work does not help you, right? Okay. Check your work, please. See that you get this. Add this number over here and divide by the 0.5. Significance of the answer, obviously, it's negative because it's rebounded off the wall. We don't know if it should be more or less than what it started with. It started with a velocity of 9 meters per second. This is negative 8. We can't really tell if that should have been more than 9 or less than 9 based on the numbers alone. It's not enough information. That's pretty much all we can get from this kind of a problem. Okay, the one significance of it bouncing off the wall is what's really important as well. Okay, let's look at this. Is all momentum and momentum impulse theory. Okay, momentum and momentum impulse theory. A 2,000 kilogram car traveling east slows down uniformly from 25 meters per second to 10 meters per second. How long does it take the car to do this if the force on the car is 750 newtons? How far does the car travel during this deceleration? Okay, how far does the car travel during this deceleration? So, for the first part, we've got a force listed. Let's go ahead and write that down. Okay, we know that the car is a mass, or has a mass of 2,000 kilograms. It slows down. So what's bigger, VI or VF? VI has got to be bigger if it's slowing down, right? So VI is the 25 then, you know that, which makes VF 10. You know the acceleration is going to be negative, but we don't need the acceleration here. This problem simply says determine the time it takes. How long does it take? So you could find the time it takes in multiple ways. You could actually use F equals ma with Newton's laws if you wanted to. I would use a momentum impulse theory because it's pretty straightforward by doing it that way. But you could use Newton's laws if you want to. If it's the midterm exam and this is a problem, you want to use the Newton's law F equals ma, that works. That works here as well. Replace A with VF minus VI over T. Yes, any of the ways you learn throughout the year could be used in part 2s. Okay? How about the force? What's the force in this problem? Yeah, be careful though. Is it 750?
Yes.
It slows down, so what kind of a force is it? There you go. Okay? Remember guys, if it's moving with a positive velocity and it slows down, the force has to be negative. Think about it. There's no way. If you give a positive force to it, it means you're helping it move faster. You're making it move much faster by giving a positive force. A negative force is like hitting the brakes in your car. The brakes are a negative force. The accelerator, that's a positive force. So at this point in time, we could use the momentum impulse theory because we're trying to figure out how long it takes for this to happen. So we've got our formula. Delta P equals F times T. Delta P is mVF minus mVI equals F times T. Now, I'm not going to plug in this problem because I'm looking for T. So it makes sense to solve for T. It's very easy to solve for T. In the last problem, we were trying to find VF. And just to show you guys that it didn't matter if I plugged in numbers, I did that earlier. But in this kind of a problem, you should definitely solve algebraically because it's very easy to solve for T. Just divide by F on both sides. Okay, there's your solution for T right there. mVF minus mVI all over the force. So all you got to do is plug in now. Okay, plug in. The mass is 2,000 kilograms. The final velocity is 10 minus the mass of 2,000 kilograms times the initial velocity of 25 which is all going to be a negative numerator, right? Look at the numerator. It's definitely negative.
You'll get positive time, so.
Exactly.
You need to know that the force is
Yeah, had you forgot that the force was not negative here, you would have had a negative time, which doesn't make any sense. Your numerator is negative, and so is your denominator. So as a result, you get a positive answer for time. Check to see what you get, please. Make sure you do this right. Everybody should be typing this in. If you're doing this all in one line in your calculator, you need to have parentheses around your numerator. Okay, because if you type that all in, and at the end you press divided by 750 or negative 750, it's going to take the 25 over here at the end and divide it by negative 750. You need to divide the entire numerator by negative 750. So put the entire numerator in parentheses in your calculator, please. Okay, if you need to write it on your paper, write it on your paper to remind yourself. What do you get for an amount of time? How much time does it take, Ant? 40 what? Seconds. Okay, the answer is definitely 40, and you should recognize your units were in meters per second, your units of force were in newtons, so everything is in basic SI units. The basic SI unit for time is indeed seconds. Okay, it is seconds. Now, this is not a collision problem. This is not something hitting a wall. This is you simply applying the brakes to a car. So it takes 40 seconds to slow down from one velocity to another. And the second part of this is saying, how far do you travel during that time period? Well, if it takes 40 seconds to slow down, it means you're probably not like slamming on the brakes, right? You're lightly applying the brakes. This is maybe like, you're cruising on the highway, you see traffic way up ahead. You start putting the brakes on, you slowly put the brakes on until eventually that traffic comes to a standstill or something, or very, very slow moving. So you're lightly applying the brakes for 2/3 of a minute, right? 40 seconds. So part B says, how far do you travel? How far do you travel? Well, for part B, we could think about the fact that we know some information. If we want to know how far we travel, we have to think back. Go back to our formulas earlier in the year. What formula represented how far you travel if you have acceleration involved? I'm writing it, but you tell me. You see anything about how far you travel in there? Say it one more time. Again, doesn't work. Remember, that's only when there's no acceleration, Chris. You can only use v bar equals x over t when there's no acceleration involved. Sam? You're close. The at squared is there, but the vi is in the beginning here, okay? X equals vit plus 1/2 at squared. So why can I use this formula? How come I'm allowed to use this? Do I know everything?
You don't know the acceleration.
I don't know acceleration.
But you can solve for acceleration.
What is acceleration?
It's 0.
What is it?
7 over time.
Change in velocity over time. So as a result, I don't know acceleration, but I kind of do. Put a little side note if you need to. Acceleration is change in velocity over time. You know the time, you just solve for it. You have the velocities that were given in this problem, so you could easily figure out the acceleration and then use that in the formula here. So either take this expression right here and plug it in for acceleration in the formula, plug that whole expression right in there, or get a number for acceleration and plug that number in. Either way works. Okay, either way works. So this becomes x equals vit plus 1/2. Oops. Make that a little closer. At squared. And this, remember, is vf minus vi over time. That's what acceleration really is. So again, I'm plugging in the expression. You could have plugged in the number for acceleration. What's interesting to note is that this problem actually becomes a linear problem in time, because the time in the denominator here technically cancels with one of the times up here, making this vit plus 1/2 vf minus vi times t. You could cancel one of these two each and see that, but it doesn't really matter. It doesn't affect our answer. Okay, so let's go ahead and plug in. VI times t plus 1/2. Acceleration is going to be 10 minus 25 over 40 times 40 squared. Again, notice there's a 40 in the denominator and a 40 squared up here. So if you want to, you could cancel one of these, leaving behind just the 40 up top.
Wait, that says 10?
10 minus 25. Yep. The final velocity, I think, was 10, right? 25 times 40 is 1,000. Because 25 times 4 is 100, right? So I tack on a 0. Plus. Now, what I'm going to do is I'm going to cancel this 40 with one of these 40s up here. Make the math a lot easier on me. 10 minus 25 is negative 15. Negative 15 times 40 is going to give me negative 600. Half of that is going to be negative 300. Giving me a total distance of 700 meters. That's a really long distance for you to be braking. 700 meters is a little more than a third of a mile. So this would be an example where you're lightly applying a deceleration on the brake pedal. You're not slamming on the brakes here. If your stopping distance had been like, I don't know, 5 meters, and the time it took, instead of being 40 seconds, had been like 3 seconds, that'd be a really good example of when you're hitting the brakes really hard. Okay, here, think about the context of the problem. It takes a while for this to occur. A long time and a long distance travel while braking. So this would probably not be a good amount of force to apply if you need to brake and there's like a car right ahead stop. You'd have to apply a much greater force, and as a result, you would stop at a much shorter distance. Okay, it's good to make sense of our answers, right? We know that like a small force means that the acceleration is not great, and when the acceleration is not very great, like here, it takes a while to stop. If you apply more force, you stop much quicker.
Is the force that you apply on your actual brakes amplified by the brakes that are actually...
Absolutely. Absolutely. 100%. So the question, it's a great question. Like, are you literally applying the same amount of force on the pedal as is being applied on the wheels? No. The amount of force you apply on the pedals is so insignificant compared to how much force on the wheels. And think about it logically, right? If your foot pressing the pedal could stop a car, it'd be like you saying, I could do this and stop the car as it's coming at you. You know what I mean? It wouldn't really work.
Full Flintstone.
Yeah, just like stick up your foot and just block. Oh yeah, Flintstone, you just put your feet down and drag your feet to stop. And the idea there is like you're using what's called a function box. You apply X amount of the wheel, and then as a result, that is amplified. It's a good word you use to Y amount of force. X is your input, Y is your output. So it's a function or like an algorithm, really.
Oh, we just did that in math.
In math class.
Yeah.
Nice. Are you studying functions right now? What
Yeah.
we did?
Yeah, we did the spooky thing.
Oh, he told us.
Exponentially.
Exponential.
Yeah.
Oh, nice. Very nice. Okay, next one. Next one. If the coefficient of kinetic friction between a car and the road is 1/2, what is the minimum stopping distance for a car moving at 29 meters per second? Okay, it's moving at 29 meters per second. And we want to figure out what the stopping distance is in this problem. So, we have to consider the fact that to figure this out, we need to figure out how long it's taking. How long is it actually going to take time-wise? So let's start listing what we know. What can I write down to start? Sean?
Have mass. 2200.
What else?
You have your mu values, 0.5.
What else?
And you have your speed, just 29 meters.
You have one other thing.
Are you stopping? Are we going to stop?
It says find the minimum stopping distance.
Oh, so GF is 0.
Good. Okay. So those are our 4 givens right now. We got initial and final velocity in UK, and we have the mass. Well, we look at this and we say, we're trying to figure out the minimum stopping distance. So we're trying to figure out x. But then we look back at our last problem and think to ourselves, well, to find x, we needed time, didn't we? Even if we use a different formula, even if we use vf squared equals vi squared plus 2ax, we still need acceleration there. And to get acceleration, you still need time. So in the end, we need to get time first. Okay, let's figure out how much time it takes. So to figure out time, we can start with our momentum impulse theory, which tells us mvf minus mvi equals. Now, F, capital F here is the force applied. How could I utilize some other information in this problem? What could I do? Yeah, very good. That's exactly right, Sam. It's mu kFn. Well, where does that come from? This is really FF. Remember, the force applied comes from somewhere. In this problem, we're told the coefficient of kinetic friction is given. So you hit the brakes. Now, in real life, cars do not, the wheels do not lock. And you don't like start sliding. But we are assuming that that's what happens here. This is called sliding friction. Remember kinetic friction we talked about? So this is not incorporating anti-lock brake systems, which cars have.
So this equation is just.
This is assuming, like, imagine you could hit the brakes, right? And the wheels lock, and you were like sliding on the wheels and like literally burning rubber.
Like a
That's what this would be.
That's like when you stop a bike when it's going.
Correct. If you stop a bike when you're riding on a bike, the bike wheels literally lock, and the bike like starts to glide, right? It starts to slide.
Or you fall.
Or you fall forward. Well, if you only hit the front brake, for sure you fall forward. Because the back wants to kick over the back. But with a car, the way a car works, if you slam on the brakes, cars are made not to lock. So what will happen is the brakes will automatically start to pump. And if anybody has ever driven a car and had to have the incident that I had, it's not very friendly or not very... It's pretty terrifying, yeah. So you hit on the brake, if you slam on the brakes, you can stop instantly. The brake pedal will do this. It'll start to shake. It's nothing wrong with that. That's normal. It's called the anti-lock brake system. If you slam the brakes lock, the car would skid for a while. It pumps the brakes automatically for you. The car knows to do that. Feedback mechanism in the car that tells it, okay, pump the brakes if somebody slams them on so that the wheels don't lock, so that they slow down gradually. It actually is much better than locking the wheels because then you glide. So our goal here is to figure out the time, but we need to recognize that F is the force of friction, and since F is the force of friction, we can replace it with mu Fn. So we can go ahead and solve this. Vf is 0, that goes away. Negative m vi equals mu k. Now what's Fn?
MG.
Why? Tom?
Because Fn equals Fg and Fg equals Mg.
That works. How do you know that that first statement is true? Why does Fn equal Fg? You're right.
Because whatever is equilibrium, since the Fn goes up and Fg goes down.
And they are in a state of equilibrium. Very good. Great explanation, Tom. So Fn is really Fg because it's in a balance, and Fg is really Mg. So we can replace Fn with Mg. There's no extra vertical force anywhere. Okay, if there was like some sort of a vertical force applied to the car, that would not be the case. So at this point in time, mass is on both sides. What can I do? Cancel the mass. Okay, so I did not really need to give you mass in this problem. It's independent of the mass. The solution, that is. Negative Vi equals mu k gt. I'm trying to get t by itself, so divide by mu kg. And there's time. Now, something we should recognize. We're going to get what kind of an answer, and it's going to seem like it's wrong for a moment. Yeah, we're going to get a negative answer here, which seems a little bit odd because it's time. But here's the problem. If we had actually plugged a number in for force, we would have put a negative number in, wouldn't we have? If I gave you the force, like this problem, we don't know what the force is. We have no idea. We know it's the force of friction, and friction's force is indeed negative. So if I gave you a number and said the frictional force was 400, you would plug in negative 400, and as a result, the negative over here for the force would cancel with the negative that's over here. But it's not there. So inherently, believe it or not, up here, where we replace negative, or we replace mu k fn for ff, we should technically put a negative sign there. And I know it's not obvious, and I always go back with this. Yeah, gravity is negative, for sure.
9.81, and then you get a negative, and then what's the time?
If you want to think about it that way, you can, but in reality, it's not because of that, actually. Because gravity is acting up and down, and we already balanced that with Fn and Fg. It's left to right that's being balanced. So if we had put a force in, what I'm saying is that this number, had we known what it was, would have been negative, right? So this term here is inherently negative, but because these numbers are all positive numbers that we use, it's going to end up being a negative over positive. So really, we need to apply a negative sign when we put in the force of friction here, and that will cancel its way down. Okay, so this negative sign needs to be there for these three steps. And I know it's not obvious when you're doing the problem, but think about it for a second. Whatever number that is, it's got to be a negative number, but because mu k, m, and g are all positive quantities we use, we're going to end up with a positive, so we have to apply this negative sign here. Okay? We're going to get a time of, what do we got here?
0.17.
What do you got? 0.17. Agree, disagree, others? I didn't calculate the time, so I'm not sure if that's right. Is 0.17 correct? 5.9, 5.9, 5.9. Did you put parentheses around your denominator, Nick?
I don't know.
No, I was way ahead. And wait, I think the whole form was wrong.
You gotta speak louder.
G is gravity.
Yes, G is gravity here.
Why?
Now, that's how long it takes. The problem said, though, what is the stopping distance? So we're again going to use this formula. The initial velocity given in this problem was 29 times the time plus 1/2. Now what's the acceleration? The acceleration is the change in velocity over time. The velocity went from final minus initial, so 0 minus 29 all over 5.9. So this acceleration is right here. And remember, acceleration is change in velocity, which is final, 0, minus initial, divided by time. That's what acceleration is defined as. That's something that we learned like chapter 1, or rather chapter 2 in the book, but the first unit of the year. We talked about what acceleration is defined as, and it's final velocity minus initial velocity all over the time it takes.
I got 85.55.
Yeah, 85 and change I got. So 85.6?
I just got 55.
5.5. I did not calculate the time when I did this for my own solution. I used this expression right here, and actually I took this expression and I plugged it in here, and I plugged it in here for time. The reason I did that was to get an answer that has no rounding involved, but I still got, I think I got, let's see, yeah, I got 85.7. So see that small change? That's because if we plug in 5.9, that's a rounded answer, and as a result, it changes it. So I plugged in this expression for time here and here, and also I plugged it in this denominator for time, and up here I left that alone. I got 85.7, but again, the idea of the answer being a little bit off is because of that rounding. Keep that in mind when you're going through these problems.
When you grade these type of things on tests, do you give us a little bit of leeway room?
Yeah, always. Have you recognized that?
Yeah.
Yeah. It's like, because what I'll do is I'll see if you rounded earlier, and if your answer's off by a little, usually I'll just check your work real quick on a calculator to see that I get the same answer doing it your way. Even if you've noticed, I've done this several times. I'll put like, you know, for part B, I'll put correct based on your answer A. Has anyone seen that? I've done that for a few of you. Because sometimes you get part A wrong, but that affects part B of the problem. So if you do part A completely wrong, but you do part B right, but with the wrong number from part A, I'm not going to double jeopardize you, right, or double penalize. So I do the calculation for part B in addition and check to see that you did it right. So it's the same idea here. Okay? So what do we want to summarize from this? Momentum is mass times velocity. The momentum impulse theory is the change in momentum equals force times time. This is all that you're really given on your formula sheet for the test. You need to take this information and you need to be able to either A, figure out momentum using this, or B, figure out like the time or the force or the final velocity using this. And this needs to be rewritten, remember, as mvf minus mvi equals F times T. That's kind of what you should get the gist of for this. Now, in class, I do problems where you have to calculate the minimum stopping distance, or I use mu k and us. A lot of the time on the test, I don't go into that much, difficult. And you've noticed that. I don't use the problems where you're finding mu on the test. This is honestly the reason I do that extra stuff is for those of you that next year might want to place into AP Physics. You need to be ready to do that kind of stuff, where you take stuff you learn in Chapter 1 and relate it to Chapter 5. You have to figure out like the minimum stopping distance using x equals VIT plus 1/2 AT squared. On your tests in this class, I'm going to be testing you on more basic stuff. So when you're studying, you should really be studying problems such as example 1 is a good problem. Example 2 is a great problem. Example 3 is a great problem. But examples 4 and 5, I probably wouldn't test you as difficult on the test. Okay, so if you want to jot that down so you know when you're studying, you should really be focusing in this notes on examples 1, 2, and 3. 4 and 5 are a little bit more difficult, okay? And it's where you relate stuff we're learning now to what we learned earlier. So maybe on like a midterm exam you could be able to do that, but for a regular test, okay, examples 1, 2, and 3 are sufficient to study. Just so you know, the example we just did, example 5, could have been solved with the work kinetic energy theorem also. So we keep discussing this point. There are so many ways to solve a lot of these problems. Projectile motion, you could use energy method or projectile equations. Example 5 a moment ago, you could have used work kinetic energy theorem or momentum impulse. Example 4, you could have used Newton's laws instead of momentum impulse. So there's other ways to solve these problems. I'm just trying to show you how to apply momentum impulse and the idea of momentum. Okay, you got about 5 or 6 questions here. 7 questions rather. Keep that in mind. I'm going to start 6-2. We're not going to finish 6-2 today. It's not going to happen. Okay, in the second period, we're going to do something else. But I'm going to start 6-2 for the end of the first period. So let's load 6-2 real quick.